Mestrelab guys for this invitation. I'm very pleased to have a chance to show some of the work I have been involved with in the past 2 years. All right, so welcome everybody who is online to this talk. I hope you enjoy it. The idea of this talk is, this webinar is to show some examples of the structural elucidation of complex small molecules using non-routine NMR experiments, so more advanced NMR experiments. I can say that I have been lucky to collaborate with several people in the past 2 years that in some way or another they have to deal with isolation of natural products and thus with unknown structures. So this actually has given me the opportunity to be involved in some really nice structural elucidation work. And here in this slide you can see some of these examples, which I will be addressing in the next few slides. And also you can see some of the experiments I will be talking about, like the adequate experiment or the LR-HSQMBC and so on. So in general, when facing the structural elucidations of unknown compounds, we have a basic tier of NMR experiments, which in most cases would include acquiring a reference spectra, like a proton NMR, obviously, and also carbon NMR spectrum is optional. And then we have 2D NMR experiments providing heteronuclear NMR correlation information, like, for instance, the HSQC and different versions of the HSQC with multiplicity editing, and more recently with pure sheaf and multiplicity editing as well, that provide information between protons attached to the directly to the carbon by one bond. And we also have proton-proton connectivity network experiments like COSY and TOCSY, and also the HSQC-TOCSY, which is not widely used, but it's very interesting experiment. We get the information about the proton-proton connectivity as a function of the chemical shift of the carbon nuclide. We also have the HMBC experiment providing long-range connectivities between protons and carbons, which allows us to establish bond connectivity. And obviously also true space proton-proton correlation experiments like ROSY and NOSE experiments. Now those experiments are used for to deal with standard compounds, and they basically work just great for proton-rich compounds. But when we are facing a more complex structure, proton-deficient compound, where the number of protons in comparison with the number of carbon atoms or nitrogen atoms or oxygen atoms is lower than 2, these are known as proton-deficient compounds. And here, this set of experiments, classical experiments, may not be enough to solve the structure. So we need to rely in other experiments, such as carbon-carbon connectivity experiments that I will talk now. And basically, both provide information between carbon-carbon connectivities. So in this slide, I'm trying to summarize what we can get from the classical experiments, HSQC or HMBC. Basically, the HSQC provides correlations between protons and carbon separated by one bond, while the HMBC provides correlation between protons and carbon separated by N bonds, being N2 or 3 bonds. Now, the HSQC experiment is the most sensitive heteronuclear correlation NMR experiment, and if we assume that the sensitivity of this experiment is 100%, then the HMBC would be only 25%. And this is because of the difference between the one bond proton-carbon coupling constant, which is at least 1 order of magnitude bigger than the N bond proton-carbon correlation. That makes the delays and the HSQC pulse sequence shorter, and then basically the losses by relaxation are less important in the HSQC than in the HMBC. So this is explains basically the difference in relative sensitivity of these experiments. those are widely used experiments for structural elucidation of standard compounds, but when dealing with more challenging compounds, we have another kind of experiments, which are the adequate experiments that provide correlation between adjacent carbons. Now, those experiments, the problem is that they are very insensitive because we are looking into signals that are between two carbon-13. So carbon-13, because of the low natural abundance of this nuclei, this experiment becomes very insensitive. Actually, the chance to find two carbon-13s attached to each other, it's only 0.01%. So that explains the relative sensitivity. It's only 1% when compared with the HSQC. However, those experiments are very useful because they provide information that we cannot obtain otherwise if we have a proton deficient compound. And we have the 1,1 adequate, which provides correlations between carbons separated by one bond, and the 1N adequate that provides correlation between carbons separated by 2 or 3 bonds. Now, again, because of the difference in the 1J-CC, this is the one bond carbon-carbon coupling constant, and the NJ-CC, the long-range carbon-carbon coupling constant, the 1,1 adequate is more sensitive than the 1N adequate. So, I'm going to introduce now one version of these experiments, the adequate experiments, that force increase in the sensitivity, which is important because those experiments are very insensitive, but very useful at the same time. So basically what we did here, we incorporated the homodecoupling that it was first published in the HSQC experiment recently for the Heteronuclear NMR correlation experiments, the pure shift version of the HSQC. But basically, we are able to remove the splitting from our final multiplets, remove the splitting due to the proton-proton coupling constant. Now, to achieve this, we use what is called BERT pole strain, which basically, shortly, it distinguishes between protons attached to carbon-12 from protons attached to carbon-13. So, in that way, we can remove the proton-proton coupling constant. We have two possible scenarios in the adequate experiment. We have one question we need to answer. What gets decoupled when we use this BERT element in the adequate pulse sequence? We have two possible scenarios. One is the case that if the proton-proton coupling constant that we want to remove has one proton attached to carbon-12 and another proton attached to carbon-13, then in that scenario, the BERT element will remove such proton-proton coupling constant. On the contrary, if the proton-proton coupling constant to be removed has both protons attached to carbon-13, the homodecoupling is only partially successful. This is pretty much the same as in the pure shift HSQC, in where we can remove all the proton-proton coupling constants except the germinal proton-proton coupling constant, because both protons are attached to carbon-13. So as you will see, in the 1,1 adequate and the 1N adequate, when we use the homodecoupling, most of the multiplets will collapse into singlets, and this is very important in adequate experiments because we are improving the sensitivity, which is paramount in these experiments. So here I'm just showing these two possible scenarios. First of all, I want to show results for the 1,1 HD adequate. So we are looking at correlations between carbons separated by one bond. Here we used ibuprofen as a model compound to develop this experiment. And if we look at the correlation from on the left, from carbon 7 to carbon 6, this is a CH attached to a quaternary carbon. So basically here the HD works very nicely, because we are looking into a signal that has one proton attached to carbon-13 and the other carbon is a quaternary carbon, so has no protons. So the proton-proton coupling constant that we are removing, it's basically one proton is attached to carbon-13, the other is attached to carbon-12. So everything collapses up to a singlet. We can see the black trace would be the doublet that we get from the conventional 1,1 adequate, and the red trace is the sharp singlet that we get from the 1,1 HD adequate. So as you can see, everything collapses into a singlet, and thus we have an increase in the sensitivity. The other possible scenario, which is on the right, is if we look at the correlation between carbon 8 and carbon 7. These are two protonated carbons, so we are looking at this correlation that has these two protons attached to carbon-13. So we cannot remove that proton-proton coupling constant because the Merck element is not able to distinguish protons that are attached both to carbon-13. So everything will collapse up to a doublet, up to this doublet between these two protons. In practical terms here, in this particular case, the conventional adequate, which is the black trace, appears as a doublet, as well as the 1,1 HD adequate, which also appears as a doublet. So there is no increase in sensitivity here. If we look at the 1N HD adequate, so here we are going from CH to a long-range CH carbon. Now, again, we cannot remove the proton-proton coupling constant of these two protons that are attached to carbon-13. But in this case, this proton-proton coupling constant is very small because it's actually a 4-bond proton-proton coupling constant. No, 5-bond proton-proton coupling constant. So it's really small, and in practical terms, it's not resolved in the final line shape. So basically, everything will collapse up to a singlet in the 1N HD adequate. Then again, we can see here that we are looking at the correlation between C5 and C2, carbon 5 and carbon 2. The black trace is the 1N adequate conventional experiment. It appears as a quartet, and in the 1N HD adequate, we are able to remove the proton-proton coupling constant, and everything collapses up to a singlet with the corresponding increase in the sensitivity. So this is how the HD adequate versions of these experiments work. As a summary, we have the 1,1 HD adequate that provides full homodecoupling for quaternary carbons, and the 1N HD adequate provides homodecoupling for all the correlations. So if we think about it, these are actually the two types of correlations that we care the most, because those imply carbons that don't have protons, like in the 1,1 HD adequate, we are talking about quaternary carbons, and the 1N HD adequate, which is the most insensitive experiment. So having said that about the adequate, I want to start showing some examples. And first of all, I want to start with this compound that it's an alkaloid by the name of Cryptospirolepine. And basically, what happened with this compound, it was reported, the original structure was reported in 1993, and basically the structure was based on some points, some important points. The most important point is that there were no correlations from any proton to the carbonyl that you can see in structure 1. So this basically meant that any proton had to be at least 4 bonds away from the carbonyl. They were not able to see any correlation from to the carbonyl from any proton, regardless of the delay optimization of the HMBC experiment. Also, it was important this rosy correlation that you can see between these two aromatic protons. But still, there were some tricky things, like for instance, an unusually strong 4-bond proton-carbon correlation. Although this is not impossible, it is very unusual to have such a strong correlation being a 4-bond correlation. And another strange thing, or weird thing, was that the chemical shift of the carbonyl was a little bit downfield for an amide carbonyl like this, actually 186 ppm 86 ppm is a bit downhill. However, they reported the structure in 1993, but what happened is that 10 years later, they cut open the sealed NMR tube and they analyzed what was in there, and they just realized that there was no cryptospirolepine remaining, and they were able to identify up to 26 degradants, being the two major ones fully characterized by NMR. So actually these are compound 2 and compound 3. And the thing is that compound 2 could be easily rationalized from the original reported structure, but compound 3 couldn't be rationalized at all. So basically that meant that the original reported structure was somehow misassigned, and that was incorrect. So therefore we decided to reinvestigate the structure of this complex alkaloid, the cryptospirolepine, and we decided to use 1,1 and 1N-HD adequate experiments to do so. Unfortunately, sample availability was very low, but fortunately we were able to work with 1.7 microcryoproof, which greatly improves the sensitivity of our experiment. So here are the results of the 1,1 and 1N-HD adequate when applied to cryptospirolepine. I'm basically showing the two possible scenarios again for the 1,1-HD adequate and the 1N-HD adequate, but here in the real case instead of using ibuprofen. So on the left I'm showing the 1,1-HD adequate. If we look at the correlation between carbon 1 and carbon 2, this is CH spin system. So we cannot remove the proton-proton coupling constant of these two protons because both are attached to carbon-13, so everything appears as a doublet. Now if we look at the correlation from C1 to C11A, this is a CH attached to a quaternary carbon, so in this case we are able to remove the proton-proton coupling constant and we get a singlet with the improving sensitivity. Then again, if we look at the 1N-HD adequate, the correlation from C1 to C4, here everything collapses up to a singlet because the proton-proton coupling constant between C1 and C4 is too small to be resolved in the final line shape. So this is just same results as we saw with the ibuprofen, the model compound, and it's worth mentioning here, very remarkable, that this data was acquired in a 700 microgram sample, obviously with a 1.7 microcryoproof, otherwise it would have been impossible. And now I want to show the key information that we extract from this experiment that allows us to revise the structure of cryptospirolepine. When we run the 1,1-HD adequate and we look at the correlation from the proton 13, proton 13 showed two correlations. One to carbon 2, which is actually the carbonyl that appears here folded because we were using the reduced spectral window in the carbon dimension, and also to carbon 13A. So basically here, this is telling us that this vinyl proton, proton 13, is 2 bonds away from the carbonyl, which is completely new when compared with the original reported structure in 1993 that you can see on the right. This vinyl proton was actually 4 bonds away, and in this revised structure, this proton is actually 2 bonds away only. So this makes the core of the molecule to be completely different, completely, it's been reorganized. Instead of a 7-5 member ring, as in the reported original structure, it's a 6-6-5 member ring. Also, you can see that there is a weak correlation from proton 13 to carbon 1, carbon 111. This is the spirocarbon. This is actually a 2-bond correlation showing up in the 1,1 adequate, and I will talk about this a little bit later. We also run the 1N-HD adequate, and all the correlations that we got from this proton 13, the vinyl proton, make sense with this revised structure with the 6-6-5 member ring. So if we go back and we compare the structure from 1993 and 2015, everything makes much more sense now, because the rosy correlation, for instance, it's still we still kind of count for this rosy correlation. What was an unusual 4-bond proton-carbon correlation, it is actually a 3-bond proton-carbon correlation. And most importantly, the strange downfield carbonyl chemical shift at 186 for the amide carbonyl in 1993. This is actually an alpha-beta unsaturated carbonyl, so this chemical shift makes much more sense. So you can see that the core of the structure is completely different from 1993 to 2015. So, and the key experiment that allows us to revise the structure was actually the 1,1-HZ adequate, which provides the key information that the vinyl proton is actually 2 bonds away from the carbon. All right, so I want to jump now into another part of my talk. I want to show another example. In this case, this is from a collaboration that we did with Emily Mevers and John Clardy from the Harvard Medical School. And here, this is a complex compound, exocyclic fungal metabolite that was isolated. And they contacted us because they were, in the beginning, they were not able to figure out the structure of this complex alkaloid. As you can see on the left is pretty crazy. Actually, from the first NMR data set, we were only able to establish these fragments here. You can see with black bonds, we can see correlations, fragments extracted from COSY and HSQC data, and with blue bonds, we can see fragments that were extracted from ACD structural elucidation chemical shift library. However, the structural elucidation failed to provide the skeleton of this complex fungal metabolite by the name of Homodimericin A, due to the indeterminate nature of the HMBC correlation. This was actually the real problem here. The HMBC experiment was too messy for analysis because everything correlated to everything. So because of that, we got the compound and we ran 40 Hz optimized 1,1-HZ adequate, which afforded the correlations that are denoted here by the red bonds. And as you can see, we were able to define pretty much the core of the molecule. And after that, which we got from the 1,1-HZ adequate, all the correlations from the HMBC were now interpretable. So we went back to the HMBC data, and we were finally able to establish the skeleton of this complex compound. And here we can see in the blue arrows, which are the most important HMBC correlation. And basically, this is showing us that we have 20 carbons in the exocyclic core of Homodimericin A that contain 14 quaternary carbons, being 11 of them contiguous. So this is a pretty crazy structure in terms of very challenging from the NMR point of view. But the point here is, again, the 40 Hz optimized 1,1-HZ adequate provided key correlations, key carbon-carbon connectivities that make things much easier for us in order to get to the final structure. Just very briefly, I also want to mention that it was not only the structure of the, finding the skeleton of this complex fungal metabolite, but also the relative stereochemistry was very challenging. And it was a nice effort, actually. It was finally assigned based on a combination of several techniques like conventional ROSI data, but also RDCs, from which Roberto Hill made an incredible webinar in the past, a trilogy actually, about RDCs, very excellent work, and also RCSA data. This is very new techniques that allows us to to define the stereochemistry. I'm not going into details here. Also, we used J-based configuration analysis. So basically, we were measuring long-range proton-carbon coupling constants. And also, we used some DFT modeling. And in combination of all these techniques, we were able to assign the relative stereochemistry of Homodimericin A. So just as a summary, we started with an unknown natural product, where we only had a few fragments, and HMBC was too messy to analyze because everything related to everything. But then after running the 1-1 HD adequate, going back to the HMBC data, and then running some advanced NMR techniques to measure proton-carbon coupling constant and to measure RCSA and RDC, we were able to establish not only the skeleton of this compound, but also the relative stereochemistry. All right, so at this point, I want to make a good point here, because as we were using more and more the 1-1 HD adequate, we realized that sometimes we can see some of the potential pitfalls of these experiments that we need to know in order to avoid any misassignment. Basically, we were using this experiment more and more, and we just realized that sometimes there are two-bond carbon-carbon correlation that show up in the 1-1 HD adequate. Now, we need to be aware of this because we don't want to take a two-bond correlation for a one-bond correlation. We just realized that some large two-bond correlations can show up, especially when they take place across carbonyls. I'll show you an example of this. First of all, if we look at the amplitude transfer functions curves calculated for the 1-1 adequate experiment, we can see here that the experiment, the 1-1 HD adequate, the 1-1 adequate experiment is usually optimized to 40 to 60 Hertz. But the other values are also possible. Let's imagine that we optimize the experiment to 20 Hertz and that we have a correlation, a two-bond correlation that is unusually large, like let's say 16 Hertz. This 16 Hertz coupling constant in a 20 Hertz optimized 1-1 adequate experiment can give rise to a response of about 90% of the possible maximum intensity. But even such large correlation in a 60 Hertz optimized experiment can give rise to a response of about 17% of the possible maximum intensity. So this 17% can definitely show up sometimes in the 1-1 adequate, and especially in the 1-1 HD adequate, where we are having an increase in the sensitivity. So the first time we saw something like that was when we were working in collaboration with Merck Co and Chris Loren from the University of Connecticut with this Spiroketal compound. This compound was very tricky because of the high symmetry. The HMBC data was very ambiguous. So we actually ended up running the 1-1 adequate experiment first. And here, basically, I just want to highlight that one of these cases where the two-bond correlation show up in the 1-1 adequate. We can see here in the middle the 1D trace from the spirocarbon 11. We can see from the conventional 1-1 adequate, we can see two multiplets corresponding to the 1-bond carbon-carbon correlation. So basically from protons 20. Those appear as a complex multiplets, as you can see, because of the proton-proton coupling constant. But also there was something that we were not sure whether it was a real signal coming from proton 13 or it was just noise. So we actually ended up running the 1-1 HD adequate. And we can see that not only the signals from the 1-bond correlation, proton 20, they not only become sharp doublets with improved in the sensitivity, they are doublets because we cannot remove this, the geminal proton-proton coupling constant. Both protons are attached to carbon 13. But we also saw a very sharp singlet from proton 13. So now we were pretty sure that this was no noise or not an artifact. It was a real signal. But the proton 13 is actually 2 bonds away from the carbon 11. So we were wondering what is going on here. So we actually ended up running J-modulated 1-1 adequate. This is a version of the experiment that allows us to measure carbon-carbon coupling constants. And we measured the carbon-carbon coupling constant between carbon 13 and carbon 11. And we found that that coupling constant is 11.3 Hertz. We also ran DFT calculations, and we got a predicted value of 12.8 Hertz, which is in pretty good agreement with the experimental value. And if we go back and we look at the amplitude transfer curves of the adequate, for a 40 Hertz optimized experiment, such correlation, such 2-1 correlation of 11 Hertz can give rise to a response of about 23% of the possible maximum intensity, which can be even stronger when we use the HD adequate version of the experiment. So this basically explains why we are seeing these 2-1 correlations showing up, and we need to be aware that those correlations are usually very large when they take place across carbonyls. Another example is on the Cryptospirolepine. I already showed that before. If you remember, there was a correlation, a weak correlation from proton 13 to the spirocarbon. This was a 2-1 correlation, and then again, this is across the carbonyl. Here, unfortunately, we were not able to measure the experimental value of this 2-bond correlation, but we ran DFT calculations and we got a predicted value of 15.4 Hertz. Now, this in a 60 Hertz optimized experiment in this case, this 15.4 Hertz can give rise to a response of a possible maximum intensity of 16%. So this basically explains why we were seeing this weak correlation, which is actually a 2-1 correlation across a carbon. All right, so let's jump into another complex alkaloid that we were working with. This alkaloid is a marine alkaloid by the name of Eudistidine C. And here what happened is that they proposed a structure. This is, by the way, collaboration with Kirk Gustafson and Susanna Chan from the NIH in Maryland. This complex alkaloid structure was proposed based on ACD structural elucidation calculations, and also after analyzing the HSQC and the HMBC data. But the problem was that the 2 phenyl moieties at the bottom of the structure, they didn't show any correlation to the top part of the molecule. So it was, we were not very confident about the structure, and we were not able to get any correlation from these 2 phenyl moieties at the bottom of the structure in any HMBC experiment. So basically, here I want to introduce the experiments that we developed in collaboration, in this case with Teo Parella from the Autonomous University of Barcelona in Catalonia. 2 experiments that allows us to gain access to weak and or very long-range heteronuclear correlations. Now, the problem is in HMBC, the intensity of the signal that we obtain depends on the delay optimization that we are using and the actual scalar coupling constant. Due to the nature of the HMBC experiment, which implies antiphase magnetization, detection of antiphase magnetization, also multiple quantum coherencies evolving during the pulse sequence, this makes the experiment not very good to see very small coupling constants with values below 2 Hertz. In order to see those correlations with having very small proton-carbon coupling constants, we developed the LR-HSQMBC first, and then the HSQMBC-TOCSY or the HSQMBC-COSY. Now, basically those experiments are aimed to provide correlations, very long-range correlations, having a very small long-range proton-carbon coupling constant. And both experiments provide the same information, but they follow very different pathways. While the LR-HSQMBC, for instance, it's based on a direct correlation between the very long-range proton and the carbon. So basically the pulse sequence is optimized in such a way that this signal, we are trying to maximize this signal. And then we also have the HSQMBC-TOCSY, which is a two-step sequence. The first step is a classic HSQMBC step, which basically establishes long-range correlations between proton and carbon, strong ones, so like a 3-bond correlation. And then this information is, we can transfer this information to a protonated spin system by using a TOCSY transfer. So the good thing about the HSQMBC-TOCSY actually is that the intensity of the very long-range correlation, like a 6-bond correlation, it does not depend on the coupling constant, the 6-bond proton-carbon coupling constant. It only depends on the initial 3-bond proton-carbon coupling constant, which is going to be strong, and the TOCSY transfer afterwards. So this is a good thing because we can get correlations from a 6-bond, like let's say a 6-bond correlation, even if this coupling constant is close to 0. Now, because these experiments are following different pathways, they are aimed to provide information for different kind of molecules. Basically, what I'm trying to say here is that the LR-HSQMBC, because of the transfer pathway is a direct correlation, there is no need for the presence of a high number of protons. So the LR-HSQMBC is going to be a very nice experiment when trying to get additional correlations or very long-range correlation in proton-deficient compounds. However, the HSQMBC-TOCSY needs a proton-rich compound to work well because the TOCSY transfer obviously needs a protonated spin system to move forward. So the idea is the HSQMBC-TOCSY would be a better choice for proton-rich compounds, for standard compounds, if we want to get additional correlations, while the LR-HSQMBC is going to be a better option for proton-deficient compounds. Now, if we go back to Eudistidine C, it is clearly a proton-deficient compound, so we ended up using the LR-HSQMBC experiment. And here we can see the results after using the 2 Hz LR-HSQMBC experiment. We were able to get all these 4-bond and 5-bond correlations that between the bottom phenyl moieties of the structure with the top part of the structure. Those correlations couldn't be obtained at all with the HMBC experiment, and you can see here these numbers 087, 034, 044. Those are DFT predicted values for these coupling constants, 4-bond and 5-bond coupling constants. They are all very small, smaller than 1 Hz, so they are really difficult, if not impossible, to observe in an HMBC experiment. However, the LR-HSQMBC provides those correlations and with very good sensitivity. So we have now those correlations, so we have more confidence in the structure of Eudistidine C. Alright, and I want to jump now into the last part of this talk, which is about an experiment that we used to solve a regiochemistry problem that we had. And it's based on the visualization of the chlorine isotopic effect on quaternary carbons. We have this reaction from the chemist. Basically, from this reaction, we can obtain 2 possible radioisomers, number 2 and number 3, and the only difference is whether the fluorine and the chlorine are ortho to each other or para to each other. So we need to know which one is which one. But here conventional methods fail because there were no NOE, any proton-proton NOE or ROSI that could help here. Also, HMBC and adequate data was too ambiguous because of the symmetry of the molecule, and they are pretty much the same compound. And also chemical shape predictions were also ambiguous because we were not able to distinguish the chlorobearing carbon from the sulfonamide-bearing carbon, those carbons that are marked with the star in compound 2 and compound 3. So, everything was too ambiguous, so we couldn't say which one is which one. So we thought that an ambiguous way to do it would be to visualize the chlorine isotopic effect on the quaternary carbon. If we are able to know which carbon is the one attached to the chlorine, then if we know that, we only need to look at the splitting, the fluorine carbon splitting of that carbon that is attached to the chlorine. If that carbon shows a large splitting with the fluorine due to the coupling constant, fluorine-carbon coupling constant, that means that fluorine and chlorine are closer to each other. Otherwise, if the splitting of that carbon is very small, that means that chlorine and fluorine are parallel to each other. In order to visualize the chlorine isotopic effect, we need to develop a pulse sequence that allows us to achieve super high resolution in the F1 dimension, because we are looking for a really tiny isotopic shift on the carbon 13. So far, the only way to do that, it was by using carbon NMR. So we can run a carbon NMR spectrum, 1D carbon NMR, and try to visualize the chlorine isotopic on the carbon. But this requires a very time-consuming experiment, because we need to acquire a super high resolution 1D carbon NMR. It also depends on sample availability, and basically it's not always possible to run a carbon NMR in these conditions, especially if we are dealing with natural products that we have small amounts. So an elegant alternative is to visualize this isotopic shift indirectly from a 2D NMR correlation NMR experiment. So we need a lot of resolution, right? So we need to minimize any distortion in the final line shapes. So without going into too much details, we need to use proton selective pulses during the INF transfer of this HSQMBC pulse sequence, and also a carbon refocusing pulse in order to have the super high resolution that we are looking for in the F1 dimension. So here the strategy was to look at the correlation from proton 5 to both carbon 3 and carbon 1, which we need to know which one is carbon 3 and which one is carbon 1. So proton 5 correlates via 3-1 correlation to 1 and 3. And when we look at the correlation from 5 to 3, which you can see in panel A, B, C, and D, this is the same correlation. The only thing that is different here is the way that we process the data. If we look at those 2D cross peaks, we can see that this carbon, the carbon 3 at 1 resonating at 105, has this isotopic, chlorine isotopic shift. So if we process data conventionally, and this is panel A, we barely see this isotopic shift. But instead, if we use resolution enhancement, and instead of using a sign apodization function, which is the conventional way to process 2D data, if instead of that we use a Gaussian apodization function, which is resolution enhancement, we can get better resolution, and we are able to see this tiny chlorine isotopic effect. Actually, the ideal conditions here are represented in panel B, and we can see that we are able to see this isotopic shift that was measured to be 0.6 Hertz. So this is super tiny effect. Now we know that the carbon resonating at 105 has this isotopic shift pattern. So this is the carbon that is actually attached to the chlorine. And indeed, when we run the same experiment and we look at the other carbon, carbon 1, which is panel E, that resonates, this carbon resonates at 120, there was no isotopic shift at all, even when we used resolution enhancement to process the data. So now we know which carbon is which one. We know that carbon 3 is attached to the chlorine and is the carbon resonating at 105. And carbon 1 is the one attached to the sulfonamide group resonating at 120 ppm. Now, because the carbon at 105 has a large splitting of 19.1 Hertz due to the carbon fluorine coupling constant, we know that this carbon is 2 bonds away from the fluorine, so we know that the compound is actually the one with the fluorine and the chlorine ortho to each other. Alright, so I think this is it. These are all the examples I wanted to show. And to finally end this meeting, I want to acknowledge all the people that has been involved in these projects. People from all around the world, actually, collaborators from Europe, Theo Parella from Autonomous University of Barcelona. I want to thank also Wolfgang Bermer from Germany, who helped to develop the 11HD adequate. Also collaborators from the US, Emily and John Clardy, Mark and Chris and Kirk and Susanna. And special thanks to the NMR team members here in Merck. I want to thank Izu, super smart guy, Ryan, who never stops working, and also Alexei, Haiyong, Misha, and Xiao. And obviously, I want to make special thanks for Gary Martin and Thomas Williamson. And I want to thank you all for being listening here online, and I hope you have enjoyed this webinar. And I'll be happy to take any questions.